Hi, everyone. I'm Hemanth. I'm one of the Cilium CNCF maintainers, and I'm a principal engineer at Microsoft on the Azure Container Networking team. So I work on a managed Cilium offering. So when you create an AKS cluster and select Azure Managed Cilium, our team manages that. So today I'm here to talk about one of the Cilium's favorite features, users' favorite features, Cilium ToFQDN network policies, and how we can improve that. And can we really parse DNS in eBPF? The answer is yes. Thank you for coming to my talk. That's the shortest talk ever. Jokes aside, why, right? Why do we even want to try and parse DNS in eBPF, right? Isn't like writing eBPF programs hard? Isn't DNS hard? Why do you combine two hard problems, right? So in order to understand why we even want to try and do this, we need to understand like how Cilium's FQDN network policies are implemented and what some of the limitations are with them. And over the course of years, we've been trying to improve the ToFQDN policy subsystem, and we've made some improvements throughout the way. But we want to see if we can push it all the way with eBPF, right? So we'll get into some details on how the DNS RFC itself, what the RFC itself says, and some of the challenges with using BPF to parse DNS. And we'll try to get into details of like how do you do loops in BPF, how do you parse streams, and things like that. So let's get started. Before we do that, like quick show of hands, like how many of you have used a ToFQDN network policy before? Oh, that's cool. In production? Nice. OK, this is going to be interesting. So for those of you who have not used it before, like here's how an FQDN policy looks like. It's pretty simple. You select which endpoints it should apply to. You specify which fully qualified domain names you want to allow traffic to. And Cilium would automatically translate the domain name to IP address and then allow the network policy for you, right? So that's pretty much a 1,000-foot view of like what ToFQDN network policies are. And before we get into the details of the talk, we need to really understand how the existing system works like. So we'll take a little bit of time to like go through what's happening today in the OSS. So let's say you create a pod on a node. You try to make a DNS request. You created a FQDN network policy. So your application tries to make a DNS request. And Cilium transparently intercepts all of these DNS requests so that Cilium can actually know the mappings between the domain names and the IP address, right? So Cilium does this by a combination of like marking packets and some IP table rules. And Cilium basically transparently intercepts that and sends it to a userspace DNS proxy, right? So the DNS proxy then intercepts these requests and makes an upstream call, DNS request, to whatever your upstream is, and gets the DNS response back. Oh, and before that, the DNS proxy also checks from an L7 DNS perspective, is the client even allowed to make that resolution, right? So if that is allowed, then it makes an upstream connection. We get the response back. Once we get the response back, we parse the response, get the mappings between domain name and IP address, send that to the Cilium agent, so that Cilium agent can do the corresponding policy map updates and IP cache updates, right? So that once the application is ready to make that request, the policy is already plumbed down to the data path, right? So once Cilium agent confirms that all of that plumbing is taken care of, the DNS proxy would then release the response back to the client that made the request, and then the application would try to make the request, and everything would work, right? But you can actually see some of the problems this architecture may have, depending on how you run your production systems. So in the OSS, until like a last version, the DNS proxy is tightly coupled with Cilium agent. So if you try to do a rollout because you're upgrading Cilium or any other operation, then the DNS proxy would go down with Cilium agent. So what that means is the redirects are still in place, but the proxy is not up and running. So your DNS request would be black hole, and you would have no resolution. So that's the fundamental problem with this model. So over the course of last 1 year, like we've been trying to improve this. We have a CFP for this, and thanks to our colleague Vipul for like driving this aggressively throughout the last 1 year. But we now have sort of a HA mode. So now what we do is we have a standalone DNS proxy which runs outside the Cilium agent. So now we have two proxies, one that is part of Cilium and one that runs outside the DNS proxy. And there is a gRPC protocol where the Cilium agent and the standalone DNS proxy talk to each other. They exchange policy information, they exchange mappings. But still, the actual plumbing down to the data path is still done by the Cilium agent alone. So what this means is, I call it HA-ish, because this works only if your application has already resolved a given domain name before Cilium agent went down. So if you make the request and the proxy is not available, you have the other proxy that can actually pass through your request, but it cannot update new policy to the data path, right? Because Cilium agent is unavailable, and we don't want two components to write data to BPF maps. So there are still some limitations with this mode, right? So how do we actually improve this? Why don't we try and implement this in BPF? What are some challenges with it, right? So historically, this has been hard. And when I've spoken to a bunch of network engineers that I really respect, they've all been telling me, like, are you crazy? Why do you want to do that? That's not a good idea. But when I talk to security folks at my previous companies and like some of folks from Tetragon, like Mahe, for example, they were a little more optimistic because they've used BPF and DNS for security enforcement. So there are a bunch of challenges with parsing DNS in BPF. We'll get into the details of how the protocol itself makes it hard. But we'll go into the details of each of these problems. But fundamentally, like the responses are dynamic. And in BPF, you need to be really careful in how you write the program. Otherwise, your verifier is going to reject them. So it's a little complicated, but we'll get into the details. But one of the major challenges was also that Cilium used to lazily allocate FQDN identities in the past. And we used to also allocate one identity per IP address, right? So that has changed from, I think, 2 releases ago, where now we only allocate one identity for an entire FQDN label. So that made it a little simpler. But we were also still lazily allocating FQDN identities until recently, where thanks to Casey for implementing this, we now pre-allocate the identities for a given FQDN label soon after you create the network policy, right? So when you apply network policy, Cilium agent receives a policy, and it already pre-allocates the identities in the Cilium subsystem. So that's one less problem to deal with. So okay, so now with those things behind us, right? Like let's take a look at like how DNS itself, how the wire protocol actually looks like, and if you were to try and attempt to write a parser, how does it even, how do we even go about it, right? And like we look at like RFC 1035. Bear with me for 5 minutes. We'll get into some few details of the wire protocol and how we need to parse and what we need to parse. And the protocol is also quite old. If you look at it, it's written in 1987. So we are combining something that was written in 1987, and we are trying to parse that in BPF. So at a high level, this is the basic set of sections in the DNS message. So you have a header, you have a question, which is your DNS name, and then you have a set of answers, which are basically the IP addresses, whether IPv4 or v6. And we have some additional details. We will not get into it now, but so this is the header exploded a little bit. So there are a few things that are important here. We'll talk about this TC bit, which stands for truncation. We'll talk about the QD count, which is the number of questions in the DNS message. And we'll talk about the AN count, which is the number of answers in your DNS response. Those are just the relevant bits in the DNS header. And if you look at the question section, there's something called QName. QName is basically the domain name you're trying to resolve, right? And the way this works is, let's say if you are you're trying to resolve api.github.com, right? So the way it works is the first you'd have the label length, let's say API, that is 3. So there would be 3, and then API, and then you would have the next length, that would be GitHub's length, and then there would be com, 3 for com, and then you would have 0, right? So you need to keep parsing until you hit that 0, right? So you need to basically somehow write a loop, right? And in BPF, like, how do you do that, right? So you have to be really specific on what kind of, what you're writing, and you need to make sure you're not exceeding the packet bounds, right? So that's the first challenge. And in terms of the actual response, if you look at it, the resource records are interesting because they actually have the answer. They have some duplicate data. Like the question section already has the QName, but your answer section also has a name section. We'll talk about this a little bit more, but the R data and RD length will actually give you the responses, which are the IP addresses. And the second challenge in parsing DNS is there's something called as compression. So what we looked at here is the QName already has your domain name, right? And then the name is basically repeating the same data, right? And DNS is mostly implemented in UDP, and you don't have too much payload to work with. So there's something called label compression. So if you've seen a label somewhere else in the packet, you basically have a pointer referencing to that section, right? So let's say if you're trying to resolve api.github.com, and in the questions QName section, you already have 3 labels, right? API, GitHub, and com. And in the name section, in part of the answer, you don't have to repeat the labels. You just have a pointer that references to those, right? So that way you can save some payload. So that's the challenge number 3. So what that means is you'll have to go to these pointers and then resolve them, right? And then this goes into some details on like how do you parse the IP addresses. This is very similar to how the names itself are parsed. You have RD length that tells you how big either 32 bits or 128 bits. You can understand whether it's IPv4 or v6. So an interesting thing about something that is written in 1980s is that they optimistically add this section called QD count, which says that how many questions are part of this message. But I've been trying to like make a request with multiple questions in a same DNS packet, but I was not able to do that. Like dig itself did not support that. So I went digging, and turns out like the QD count is actually usually 1. There's actually an RFC specifying this. You can go look it up, 9619, and the QD count is almost always 1. So what that means is maybe we don't have to actually implement compression. You just need to understand whether there is compression or not, right? And if you go back to the, let's see. So in QName, we only have 1 query name. There's an RFC to back that up. And in the name section, we have compression, so we can handle that. But in QName itself, maybe would there be compression? Let's say if I have something called api.api.github.com, would there be compression? No, because you'd have to have a pointer pointing to itself, and that's not valid. So that we don't have to worry about that either, right? So all we need to do is we just need to know whether there is compression. At least this is my read of the RFC. I'm sure there are some DNS experts. You can tell me I'm wrong. I'll happily change that. But in my implementation for this prototype, I did not have to actually keep track of all the labels that we saw and then do the pointer chasing. OK, that's fine. But we still need to solve for multiple answers. So we don't have to solve for multiple questions, but we still need to solve for multiple answers. And trying to write something where in runtime you need to figure out how many answers are present is hard because BPF, right? But there's actually quite some improvements in BPF of late that make it possible to implement logics like this. So prior to 5.3, loops had to be actually completely unrolled, right? So when you write a loop, like the compiler would like completely unroll the loop, and then verifier would check that, right? But in 5.3, we have something called as bounded loops, where you don't have to unroll them, but now the complexity is on the verifier to actually verify the entire loop, right? So even though you could write programs that are not unrolled, the verifier is still doing a lot of heavy lifting, so it was very easy to hit the complexity limits, right? But luckily from 5.17 and above, there's this new helper function called BPF loop that allows you to write loops in BPF where the actual execution of the loop logic itself is part of the BPF subsystem, and it's not part of the bytecode of your BPF program. So it's a lot easier for the verifier to check that. So we will kind of use that for this prototype. OK. So remember I was talking about this truncation bit. This is one bit that made my life hard. So it turns out, like when you have UDP, and if you have like a lot of answers, and if you're exceeding that UDP packet size, then the DNS servers would generally set a truncation bit to indicate that I have more data to tell you, but I cannot because I'm out of payload, right? Then the expectation from the clients is that you make a request now with TCP, right? Not with UDP, with TCP. Now, how do we deal with that, right? Like the problem with TCP is now you can have multiple packets, and your response might be split in multiple packets. If you've ever tried to understand how TCP state machine works, I will not attempt to do that in BPF, right? But luckily, this is a solved problem thanks to John Fasterbend, who implemented something called a new BPF program type called SKSKB, which lets you work with sockets and kind of implement two types. There are actually two types of attachment points. There's something called stream parser and stream verdict. So you can, and we use a combination of sock map and sockops to register and collect the sockets. Actually, let's go to the diagram. So now what we're trying to do is, if your client switches to TCP, how would you still capture the response, right? So soon after your application tries to make that DNS over TCP request, you would have a socket, you would have a connection established. And soon after you have a connection established, you can write a sockops BPF program that would get a callback. And under that callback, you can hold a reference, you can get a reference to that socket and add it to something called as a sock map. A sock map is a special type of a BPF map that lets you do interesting things with socket events, right? So the first part to this puzzle is writing a sockops BPF program, get a callback soon after a connection is established, and dump a reference into the sock map. And after that, we can attach two programs using two different attach types. The first attach type is called stream parser. I actually call it stream parser BPF program, but it's an SKSKB BPF program with a stream parser attachment type, right? So what this attachment type does for us is every time you receive a message on the socket that you added to this sock map, you would get your program would be invoked, right? And the only job of the stream parser BPF program is to just tell the kernel whether we've received the full message or not. So there's an RFC that specifies how DNS over TCP works. And the interesting part is there are first 2 bytes that tell the entire message size, even if it is split across multiple packets. So what we do is in stream parser BPF program, we wait till we get the first 2 bytes and get the length of the entire DNS message and return that in the stream parser BPF program. And then the kernel would call the stream verdict BPF program once the entire message is ready. And in that stream verdict BPF program, we can now implement all of the parsing logic using BPF loops that will allow us to parse multiple answers. And remember, like I mentioned, that a feature implemented by Casey that made it possible to pre-allocate identities. So if you create a FQDN network policy, we already have identities, right? So all I did was I moved those identities into a BPF map. I should have added that BPF map as well here. But so the flow basically goes like this. You make a request. You try to establish a connection on the socket. The SOC-ops program captures that, dumps it into a SOC-op. This SOC-op map already has 2 BPF programs attached to it, and we are able to parse that. And in the parser, we basically get the queue name and look up that BPF map to know what the identity for that domain name is, and we update the IP cache. And I'm assuming IP cache, everybody understands what IP cache is, but IP cache is basically something that Cilium uses to maintain a mapping between an IP address and identity, and your policy subsystem looks up this IP cache at runtime, right? And once we update that IP cache, we're done, right? So everything necessary for the policy is already plumbed, so you can go ahead. So let's, thank you. So let's go and see a demo if my connection still works. So how do I do this? I have to replicate. All right. So what I have here is a kind cluster. So I basically have 2 node kind cluster with a pod called nettools, which we'll use to make a DNS request. And we have a policy called, we have a policy which basically whitelists Microsoft.com and API.github.com. And there's something that I had to do to disable the userspace DNS proxy. So we'll see if that's actually disabled. We can check that with Cilium. So I'm exec into one of the Cilium agents here. So let's do Cilium status -- verbose. So you can see that there are 0 redirects here. We discussed that how Cilium intercepts the traffic to the DNS proxy. Those are with redirects. So there are no redirects here. So the DNS proxy is not getting any data. But we do have identities that are already pre-allocated for this. So let's see. Cilium BPF FQDN identity list. This is from some of my testing, but you already have pre-allocated identities. Now we're exec into one of the, before we do that, let's look at some of the BPF programs. So let's see BPF tool. So we have a SOC-ops program on 2 of the worker nodes and the control plane, and let's see. So there's something called type 14, which stands for SKSKB. I shouldn't have restarted my container, but if you upgrade to the recent version of BPF tool, that'll tell you that's an SKSKB BPF program, and with the attached types. So we have 2 stream parser and stream verdict BPF programs. And here let's trace, let's get the trace pipe. And now if we do curl -v Microsoft.com. All right. So the trace log is basically what our BPF parser is doing. So we are parsing the DNS query. We are parsing the queue name. We're looking up the identity. We found that it's compression. There is compression in the answer. So we don't have to actually resolve the compression. We just need to know there is compression and seek forward. And we know that the RD length is 4. And we have an IPv4 answer. And we updated IP cache for that IP address to that identity. And similarly, we also have a v6 resolution. So RD length is now 16, and we update in the IP cache for that too, and we're able to do that. Now let's say if we try to talk to google.com, that would not work. Yep. All right, so that's the BPF-based DNS implementation. So what are the next steps? Watch out for a CFP. This is still a prototype, but we'll publish a CFP to get some feedback from the rest of the maintainers. And we'll likely talk about this in the Cilium's Dev Summit that is going to happen later today. So we also want to try and implement basic glob string matching so that you can do like star dot something and get some performance numbers. And another interesting thing was Cilium has something called DNS visibility policies. And if you create a visibility policy, the traffic still goes through the DNS proxy. So hopefully, like as a nice side effect of this, we could do proxyless DNS visibility. Yeah. Cool, that's pretty much what I had. Any questions? You can find me as Hemanth Malla everywhere on all socials. And if you're interested in working on problems like this, we do have open roles in Azure Container Networking team. You can find those roles on careers.microsoft.com. And do share the feedback if you have any. And I'll take questions now. Yes. Can someone pass around the mic? Or there is a mic there.
Any visibility in metrics? Now, DNS people are usually paranoid about, given what happened 2-3 weeks ago.
Yeah.
Now, when we are trying to contain DNS within intra-Kubernetes networking, how do we get depth with respect to DNS retries? How do we get depth into security, zero trust, for example, or if you're going in the direction of microsegmentation, how can we be confident that DNS is not hijacked? So a two-part question, to be honest. One is metrics and quote-unquote insane visibility. Two is hijacking of DNS requests, because you have other resources, right? Like enterprise DNS protection services where you can sync whole domains. You can get more visibility into who's trying to change resolve.conf, for example. So two-part question, though.
Yeah, thanks for the question. So in terms of visibility, like Cilium the Cilium's data path already exposes a lot of metrics, like very rich metrics in terms of what the network policy subsystem is doing. So you can actually see network policy drops, drop reasons. So we could basically extend the same metrics to also include DNS metrics. So today, all of those metrics are exposed from the user space proxy, but there's nothing stopping us from implementing some telemetry as part of the parser itself. And I would say like it's also a little more robust because you cannot resolve something without the kernel seeing it, right? Yeah.
Thank you.
So we have time for one more question, and then we need to keep going. And Hemanth will be here the rest of the day, too, so you can talk to him.
Hey, thanks. Great talk. Where does the IP cache live? Is it in the DNS proxy?
Why does it have to be, sorry?
Where does the IP cache live?
Yeah, so it's part of a BPF map. So it's on the same node. So you just maintain a mapping of all the IP addresses that are resolved to the identity. And Cilium also does that for existing workloads. So if you have workloads that are already created, Cilium would allocate one unique identity per a unique set of labels. So all of that lives in a BPF map. So when Cilium's policy BPF programs are trying to enforce policy, it's just a map lookup.